algorithms, and starting with you have seen this before when Yao Liang talked about proximal methods. So f of x here is some differentiable function, need not be convex quite yet, and you can run this thing called projected gradient. Some people call it gradient projection. It's an amazingly nice method to the extent that actually even if f is non-convex, sometimes even if f is discontinuous or defined over discrete sets, you can create analogs of this gradient projection method. So you can try to build on this gradient projection style idea in all sorts of spaces. Most of the analysis, rate of analysis, and stronger theoretical characterizations we will only be able to provide for the case that f is a convex function. But just to keep in mind that if nothing else comes to your mind, this is one method that is always a good thing to try out. And I think Yu Chang also already talked about an even simpler related method in recitation. I don't know how many people went there. He talked about Frank-Wolf methods. And towards the end of this month, there will be a lecture on Frank-Wolf methods in general, which are, you can say, even simpler than gradient projection. But the idea is similar. I already covered that when I told you about descent-based methods. So slight generalization of the projected gradient method is called proximal gradient, which also I'm sure you've seen in Yao Liang's lecture. So let's just, I'm stressing here that here pi is a projection operator which denotes orthogonal projection onto x. I might have briefly mentioned some properties of the projection operator already in lecture 1. And I'm calling it orthogonal projection. So it really does direct orthogonal projection. And the proximity operator that Yao Liang talked about is the one which is Euclidean proximity operator. And by stressing those words, I just want to suggest to you, yes, of course, it is entirely possible to think of methods with non-orthogonal projections and non-Euclidean proximity operators. I might briefly mention those at some point later in the class, but it's not critical for today. So just to kind of look back quickly at high-level motivation, where this might have come from, some of the details that I'll show right now, they will become apparent. The notation will become apparent as we proceed through today's lecture. So this is one way which I like to think when trying to create new iterative methods for optimization, is figure out some reasonable looking condition that characterizes optimality, and then try to see if out of that characterization you can create an iteration. And of course after that a lot of hard work is required to prove that this works, but in the playful mode of designing methods. So when I say if x star is optimal, so assume here f is convex for the moment. So for that problem, or let's just actually look at the slightly more general problem. Let's assume f is differentiable and h is maybe not differentiable. So if x star is optimal for that problem, so I'll just keep it written here that most of the time we have this fx plus hx. Very frequently when I write this, you may assume that this is differentiable and this one is not differentiable. So an optimal point satisfies that optimality equation. I'm using shorthand P for prox. So how do you derive that? It's fairly easy, right? Everything is convex, say, just take first order derivative condition. That's the inclusion. Because it's an inclusion, it doesn't hurt me to scale it by alpha. So when I add x star to both sides, it's still the same inclusion. You rearrange a little bit. You don't have to worry about the full detail of why am I doing this. Within half an hour we'll see that this is a reasonable way to be doing things. But just to show you where that thing fell out of. So we wrote x star minus that difference as that inclusion, and if you could invert that inclusion, then you get an equation for x star that should be satisfied, that x star satisfies. X star is an optimal solution of the problem. And this thing, that inverted operator, that is called proximity operator. So what we have done is just rearranged the optimality conditions of that problem and written them as, you can call that a fixed point equation because x star occurs on both sides. And many times when you see such an equation, you might think, well, this equation is satisfied at optimality for all positive alpha. Can I just now iterate? Can I pull out an iteration out of that? And that thing suggests the following iteration, which is known as the proximal gradient method or forward backward splitting method. So that's one way to arrive at it. And we'll see this type of symbolic manipulation as a way to arrive at several such iterations. So you might ask, of course, why does that iteration work? Probably you've seen some of that. I'm going to quickly summarize here just one proof strategy of analyzing these methods. And in the lecture notes corresponding to today's lecture, I'll put in few more simplified details of related proofs. So let's just look at a very simple proof why this works. So this iteration, xk plus 1, iterates that prox operator. That's the proximal gradient method. We try to write it in a notation familiar to us from gradient descent, assuming you've seen proof of convergence of gradient descent in your basic class. So I just want to forcefully write it like that. So what does that G look like? G is some vector. So just manipulate stuff and write it in a format that is reminiscent of just gradient descent without any proximity operators or constraints for projection operators and so on. And in case, I hope all of you remember, if the function h is an indicator function, then its proximity operator is nothing but the corresponding orthogonal projection operator. So that's why I'm just showing details for the prox operator. It includes gradient projection as a special case for you. So that G thing is actually given a name. Nesterov calls it gradient mapping. Some other people do too. It's like a gradient-like object. We don't really have the exact gradient with us, but we have something which for us behaves like a gradient. And this insight is actually more in hindsight. So once you try to do a proof of convergence of gradient descent, and you see that, okay, the gradient gives me a descent direction. In that direction, at each iteration, I can make such and such amount of progress. And when trying to compute that progress, you prove certain inequalities which tell you how much descent you've made. You try to mimic that proof structure, but without having access to a gradient. So you try to see which object do I have. It falls out of the algebra, and then in hindsight you try to give it an interpretation. Okay, this is a gradient-like object. But this way of thinking is quite useful when you're creating these descent-like iterations. If you manage to create an iteration, this one is with the prox operator, you might have some other operator. You run one step of the iteration, and you try to see if after running that step somehow you can measure descent using this different operator. So here we have a proxy for the gradient. Let's call it gradient mapping, and it's just, comes up by rearranging those things. And one high level idea why you might, which thing might be a good candidate for your gradient mapping is when you have an optimization problem, you have several ways of characterizing optimality. We already showed that this equation has to hold at optimality, which means if x is optimal, then that gradient mapping disappears. So in the unconstrained case, that's exactly what would have happened to the gradient. So in fact, if you look at the proof on the previous slide, you can look at it again. It in fact says that if x is locally optimal, then also the gradient mapping disappears. That gradient mapping, only the if and only if part depends on convexity of f. Otherwise, if x is locally optimal, then it disappears. So that means if you're trying to now use a proximal gradient type approach to minimize a non-convex function, you can do that by still using the same kind of iterative structure, because at least you're trying to get to a stationary point. So that optimality condition works out here also. And you might meet one of these analyses on your homework to see how much of this stuff carries through in the non-convex setup. Okay, so just, I think I'm going a little too slow, so let me gradually speed up just to tell you how a standard convergence analysis of these proximal methods looks like. And probably, I don't know if Yao Liang covered convergence proof in his lectures, but let's just quickly look at the proof structure. And in the lecture notes corresponding to today's lecture, I'll put in a couple more proofs which are based on this structure but slightly more complicated. So now we are trying to do gradient descent or proximal gradient descent. We assume that the gradients of f, so we are minimizing fx plus h of x, we assume that the gradients of f are well behaved. So you assume that the gradient is Lipschitz continuous, which means gradients of vectors that are close to each other are not too far from the points themselves. Or another way of looking at that is that f has somehow bounded curvature. Another way to look at it is that the gradient doesn't vary too rapidly or it doesn't fluctuate too crazily. All of these are in some ways a priori ways of saying that I'm trying to use gradients to do optimization. The gradient had better not fluctuate too crazily so that I can control how the procedure runs. So that's why this typical Lipschitz assumption on the gradient is thrown in. Interestingly, when people look at interior point methods, we might look at some of those later. There you have something called a barrier function, which actually is not Lipschitz continuous. So you had to stop thinking Lipschitz continuous to invent a new class of methods. So I'm just saying every assumption limits your thinking, but it also gives you something. So we'll stick with this assumption for now. So the most important thing that this Lipschitz assumption gives us is that locally any differentiable function with Lipschitz continuous gradient called CL1 can be upper bounded or even lower bounded by a suitable quadratic function, which is really nice. So f is just differentiable here, f doesn't have to be convex. You can prove this inequality, which I'll do shortly. I call it the descent lemma, and we'll soon see why we call it the descent lemma. It's by far one of the most important lemmas about Lipschitz, about CL1 functions. So for convex f, you actually also have a lower bound. Interesting to compare that this is a quadratic upper bound, you have an affine lower bound. So this inequality is missing in non-convex functions, which means anywhere down the proof, wherever I end up using this type of inequality, that proof is not going to go through for non-convex functions. But wherever I rely only on the first one, that also continues to hold for the non-convex guys. So let's quickly prove that descent lemma if you haven't seen a proof of that before. It's a very pretty simple proof. So if f is CL1, you can take, it's once differentiable, so you can take Taylor expansion. So you write, expand f around point x. You write that integral form of Taylor expansion. Now, after that, just a few simple steps of algebra, I guess. So there are various ways to do that. I guess the easiest is just add and subtract the same thing from both sides. So now the left hand side is in the form we want, the right hand side is something. After that is just really simple algebra. Once you take absolute values of both sides, apply the triangle inequality, you get that. After applying the triangle inequality, what should you do to the inner guy? You just apply Cauchy-Schwarz, right? Once you've applied Cauchy-Schwarz, what is the last thing that remains to apply? Now you apply your assumption that gradient of f is Lipschitz to get rid of this term. So you just get that, and it nicely simplifies out to this particular formula after integrating. So very easily, using nothing other than just standard Taylor's theorem, triangle inequality, Cauchy-Schwarz, and the assumption of Lipschitz continuous gradients, you get a quadratic upper bound. This upper bound is really very nice to have. So let's see a corollary of the niceness of this upper bound. So I'm using this notation here. Remember, we are just running this iteration. Xk plus 1 is xk minus alpha k, the pseudo gradient at point xk. For now, I've just written it as y is x minus alpha g alpha x to get rid of subscripts, but you can interpolate the subscripts back in if you please. So let's try to see what happens after we made one proximal gradient step. What does the objective function look like? So you just plug in that y into this little inequality there. We get this upper bound, fine. So far so good. So alpha is supposed to be thought of as a step size to tell you how long steps you will take using this pseudo gradient. So if alpha is small enough, say alpha is smaller than 1 by L, then that alpha square L will sort of cancel out. So you actually get this simple quadratic upper bound. And why is this useful? So what we are trying to do is, we are trying to see what kind of progress we might have made after taking a small enough step while using this pseudo gradient. I'll just call it gradient mapping or pseudo gradient interchangeably. And you know that the function has Lipschitz continuous gradient, so the gradient f that is sitting inside the gradient mapping is not arbitrary. So the amount of progress or the amount of perturbation that has happened is not going to be too large. So what is it? So you first see that, okay, the value at nu f is at least bounded by that quantity. Now you want to turn that bound into something more useful. So what now you're trying to do is, okay, it's bounded by some quantity, but intuitively, if I am running an iterative method and I have not yet converged to a minimum, it is quite feasible to believe that if I take a small enough step, or there might exist a small enough step that allows me to actually decrease the value of the objective function. If not, then of course I'm already stopped at a minimum, right? So it is reasonable to believe that. So what you want to do is, out of this somehow pull out to show that with your reasonable choice of alpha, after one iteration you can actually decrease the total objective function value. So one thing, there's one slight thing to note here. This inequality is for f, whereas we are minimizing f plus h. So what you want is, you want to descend not on f but on phi, which is f plus h, because that's what you're minimizing. So that part I have actually left as a small exercise for you. That exercise is basically just rearranging this important corollary that we have obtained. After that, it's merely rearranging a few things, adding h to both sides. It's a nice little exercise. And what it says is that for any z, this should be read as then phi of y. For any z, phi of y is upper bounded by that quantity. And this lemma now turns out to be very handy for us. So I've written the word prove there because that lemma is best appreciated once you prove it yourself. And you might then quickly recognize a pattern that, okay, if f is non-convex but h is convex, a similar lemma might more or less go through. So it's really good to prove it yourself to see the weakest conditions on f and h under which such a lemma holds. And our goal is to see if it tells us how much progress we have made. So now just pick some nice z. So for example, if z is equal to x, something very nice happens, right? So if z is equal to x, okay, sorry, I made a slight notational change. I am writing x prime here instead of y. That was an unfortunate notational change that I made. So now just plug in z equal to x in that. That thing disappears. So you actually see that phi of x prime or phi of y is smaller than phi of x minus something that is positive. That's the nicest thing. So if you're sitting at x, you move to x prime, and that alpha is small enough, you actually make descent. And this strict descent essentially suffices to show that we must have convergence, where of course I haven't specified what I mean by convergence. So essentially this is showing your function, the function values that you're generating, phi of x1, phi of x2, phi of x3 and so on. There is strict descent. So as long as the true infimum is bounded below, it doesn't go off to minus infinity, the sequence has to stop somewhere. So that's all I mean by convergence. So that's a good thing, because to make such a claim, you do not have to really so far invoke convexity. For the previous type of lemma, for this more general lemma, you might need to invoke convexity, but you can actually even attain descent without convexity. So important thing is, now getting convergence out is fairly easy. Slightly harder is characterizing how fast you converge. Yeah.
But what can we say about the norm of g alpha of x? Is that like this?
So the only thing we know is that, that's a very good question. We know that suppose everything is convex, g of x has to disappear at an optimum.
Right.
So it should shrink.
Right.
How fast it shrinks is not so easy to say. But at an optimum it will disappear, and you can get some bounds out. But what we are trying now to do is, it would be good to see the speed at which the norm of g shrinks, but what we are trying to see is at what speed do we decrease the objective function phi.
But isn't the speed at which we decrease the objective contingent on?
Sure, means they are. It's just that when we write a statement, we'll just write it in terms of for phi. So just another little toy thing you do with that lemma. So let x star denote an optimal x star. So you plug that x star instead of z. So f of x star plus h of x star will be phi of x star, the optimum value. So you get phi of x prime on the left minus phi star is less than or equal to that quantity. So that's just rearranged the lemma on your previous page. Now we'll see an important technique which people in various disguises they use now and then when trying to analyze speed of convergence, is to see, okay, we have managed to see how far phi of x prime is from the optimum. you try to, when trying to now determine the speed at which it decreases its distance to the optimum, often an attempt is to try to rearrange your bound to yield ultimately a sum that can to yield quantities that are amenable to a telescoping summation. So this happens actually several times. I might, once we discuss ADMM style methods, I'll show you again the same idea happening but in a more elaborate framework. So you just rearrange things here, nothing special happened. I just pulled out 1/2 alpha and rearranged quantities. So the first, so it's just a rearrangement. That the reason is because our iterations are using x minus alpha g alpha, so I wanted the alpha to sit together with g, that's all. And that's just a slight rearrangement. All it shows is that the change or the distance of phi after one step, its distance to phi star is of course going to depend on your step size, which actually shows you that actually your step size better be as large as possible. Otherwise this quantity, as alpha goes to 0, this kind of becomes uncontrollable, right? So now we have shown that this change is just is bounded above by this difference. So usually means it looks nice and clean. The hard part is often coming out with which version of the quantity to analyze. So often for all these gradient based methods, if you try to analyze them, the version that turns out to be somehow ultimately most amenable to analysis is quantities that try to directly control sometimes this thing is easier to control. So these things are sometimes called Lyapunov functions. It's just what particular quantity are you trying to control or measure your progress by. And for many of these proximal gradient family methods, the upper quantity turns out to be easy to tackle. So you were saying something?
So you're saying that it's better for the step size to be as large as possible?
Ideally, whenever you want fast convergence, you essentially want as large steps as possible.
Okay, but if you have a large step, then also the numerator will be larger, right?
You mean which numerator? Oh, you mean here? It could be in some sense. I'm just saying, you're say already sitting at x prime. Means, see, if alpha is very large, you can see from that one much more clearly, right? Your descent is upper bounded by something that depends on the minus of alpha. So if alpha is very large, the chance of having large amount of descent is higher. Of course, that upper inequality only holds for alpha smaller than equal to 1 divided by the Lipschitz constant. But intuitively, trying to have alpha as large as possible is important. And this idea actually goes further. Right now, I'm using a Lipschitz constant L, which is the same big worst case L on the entire space. It could happen that your function locally sometimes has better Lipschitz behavior, so you should actually truly be exploiting local properties, because this method is completely local, right? It's just limited for the proof by putting a global L. So that's why this intuitive idea that it try to make as aggressive alpha as possible, that's where it comes up. So okay, after that, whenever you see positive quantity minus positive quantity, that raises your hopes that okay, the analysis is over, because now for x prime, pick the new iterate. This is x prime. For x, plug in xk, fix some constant alpha. So I'm not using alpha k changing from iteration to iteration to make my analysis easier. Let's just fix alpha to be a constant at each iteration. Then just add all these inequalities for all values of k. So you just add all of them, and that's what you get. And what's the nice thing here? Well, as you might easily see, right, that summation telescopes very nicely. So the last quantity is negative, you can chuck that off to get this bound. That, okay, after these k steps, my distance, the total error or total distance that I'm away from phi star is not too bad. And because phi star is actually a decreasing sequence, it then follows that you can write phi at xk plus 1 minus phi star is just is less than 1 by k of this total summation. So this is the well-known famous 1 by k rate of convergence of proximal gradient method. But analysis is quite clean, I think. It's not as messy as analysis of other such methods, but unfortunately this, along with subgradient method analysis, those are amongst the only such simple analysis. The others are much messier. But so this is famous 1 by k rate, and it's not so easy if your f were non-convex and h is convex, and you still want to run proximal gradient like I usually do in my problems, then it's not so easy to come up with such rates of convergence without complicating things substantially. So it might be easier than to control some different quantities. So a lot of this prettiness, simplicity happens because convexity is helping you. And at a high level, the study of convexity or the study of inequalities, they are very closely related, almost the same subject, more or less. That's why it helps you a lot. So this is the famous 1 by k rate, and even though this thing doesn't, you're supposed to have seen these things in a prior course, I still find the proof technique to be really clean and pretty, so I put it up in the slides here. For CLN convex functions, the actual optimal rate is 1 by k square. It's not 1 by k. So this ordinary method doesn't achieve the theoretically best possible rate of convergence. And even if you were to throw away the prox operator and throw away projection operator and make things unconstrained, gradient descent by this analysis will converge at 1 by k, and that's also not optimal. So there is a variety of methods called accelerated proximal methods. One version of those is here. So the framework originally, the genius idea originally comes from a 1983 paper by Yuri Nesterov and some other variants that he thought of in 2004. Then some Amir Beck and Mark Tebul, they made something called FISTA that you might have heard of. That's essentially that method. And the analysis of these things is not so transparent. Paul Sang gave, to my judgment, amongst the cleanest analysis of these methods. And if you ask Yuri Nesterov, he himself says that whatever way of analyzing or why he came up with that, he doesn't have a geometric explanation for that. So that is derived in some sense by reverse engineering and brute force algebra rather than some, there is maybe some geometrical explanation, maybe one of you finds that. I don't have a geometric understanding of that thing, but neither does Yuri. So some remarks here that it uses slightly extra storage. It uses one extra vector here, or actually two. You have to maintain this history. So these methods, so okay, that's worth remarking about here. So normally when we were running gradient descent style methods, xk plus 1 depends on xk directly and just on xk. This iteration is depending on xk and xk minus 1. So these are called multi-step methods. It is a two-step method. You can imagine if you wish to construct some crazy method that you might want to use more than two steps. Doesn't really help because already using two steps gets you at the lower bound. So 2 steps makes you optimal. However, you might think that maybe using multiple steps may help empirically. So one pseudo way of using multiple steps is when we study methods like quasi-Newton methods. There you are using several vectors and several gradients over several iterations to estimate the Hessian, but in some sense you're using a lot of information. So, but theoretically this already achieves the best. And you get that nice little inequality for that. And I'm not going to, we've seen one proof, I'm not going to go through the proof of this thing in class now, but I will put a clean little proof in the notes for you to see. And if you recall, at some point I had talked about another class of multi-step methods when I talked about descent-based methods, where I said, a general gradient descent without constraints could be thought of as some step size with some descent direction, where descent direction had to make negative angle with the gradient. So that was the generic framework I had once mentioned, and I had maybe at that time told you that there exists a so-called magical choice of step size called Barzilai-Borwein step size. I don't know if you remember that. This is in the first lecture that I had on gradient descent style methods. But anyhow, in case you remember that, just for your reference, that method also is a multi-step method. So the idea of using these multiple steps seems to have helped several people. There is some other method in the literature called Boris Polyak's momentum method. People used to use it back in the day also for backpropagation to give it more momentum, whatever. That's also a multi-step method. All of those things were seen to work quite well, and they had good analysis of rates of convergence locally. Maybe that's why they were kind of motivating ideas in Yuri's mind when he came up with this multi-step method. Okay, so that is it for the prox grad and accelerated proximal gradient method. You can actually just implement that and run it. It works reasonably well. So now we'll make a switch to a different language of talking about exactly what we have been talking about, but with slightly different notation. Just so that I find the notation convenient many times. It's not always the best thing, but I find it convenient. So that notation is basically the language of monotone operators. So it's because these ideas of descent style methods, proximal style methods, the French school likes to talk about these using language of operator theory, etc., etc. The optimization people in general, they like to always talk using subgradients and subdifferentials, and essentially this is just a different language for talking about subdifferentials of functions at the heart of it. So, but it's okay to know the second language also. It sometimes helps notation. So the first question is maybe a pseudo explanation to why do we call the proximity operator an operator? Where does that name come from? You can give, of course, any kind of explanation, right? One of the explanations is maybe this. So if H is a closed convex function, so it's a lower semi-continuous convex function, then, then this operation is another way of writing the prox operator. And I'm going to, in the next, maybe, let's say 30 minutes, look at what all these symbols actually mean. Just to show you maybe some justification of why we've been calling it a prox operator so far. So suppose this operator, so one way, by operator all I mean is, some transformation which takes a vector and turns it into another vector, okay? Normally you are accustomed to thinking of matrices, operates on a vector and turns it into another vector, but matrix is a linear operator. Technically speaking, the word operator is limited to linear objects, but people abuse that terminology. So now even this non-linear transformation is called an operator. So anyhow, let's do that. So if this is single valued, then if x is equal to that equation, then you can take its inverse. That means y belongs to that. we've seen this previously. So this is the same as y belongs to x plus that subdifferential, or which is the same as x minus y plus that subdifferential contains 0. And I showed this here already because I think Yao Liang covered this in the prox lecture. So, and what is that last line? That last line is nothing but optimality condition for what defines so-called prox operator, right? Just differentiate it and you get that last line. So just rearranging the optimality conditions. So in some sense, the prox operator is very intimately connected to the notion of subdifferential, the Euclidean prox operator, that is. So let's look at a little bit of this operator language. So this is the advanced part, but this is the easy part of the whole lecture. The advanced thing is only we are using advanced words, but intellectually, or rather from the challenge that it poses to you, it's not so as advanced as the other things. So let's look at some other language. So subdifferential can be thought of as a set valued map. It operates on x, takes it into a set of different values. Set valued maps are denoted usually with double arrows in math literature. So it just takes single x and returns a set. So just notice slight typographical convention here, right? The left hand side is just partial of f. It's the operator that takes x into partial of f evaluated at x. So that's the notation. And so you have probably looked at, maybe already in 8th grade or 9th grade one sees this relations, right? When you start looking at functions, relations first time in your life. So it's really the same idea. A relation on R or here is just a subset of R cross R. For us, because we are grown-ups, we are looking at Rn cross Rn, not just R cross R, but not that much has changed here. So obvious empty relation, okay, it's the empty subset. Identity relation, x maps to x, all those. So one way of thinking of the identity relation is like set of diagonal tuples in that product space with fancier language. 0 is that. Subdifferential is the most interesting for us in the language of relations. It's just this set, x tuples. So the first thing is on which R operates, and the second thing is its result. So I'm just collecting those as tuples. So that's the subdifferential as a relation. And when I write R of x, it's just from analogy. The way we wrote subdifferential of f of x to just mean the vectors which lie in that relation. So it's just really so far nothing but notation. But notation can be useful because a lot of the time whenever you are trying to analyze mathematical quantities, coming up with good notation goes a long way. Means it's one of the harder things. And once you have good notation, then suddenly many things become transparent. So it's you have to maybe bear with this for a little bit. And this notation was created because people thought that, okay, I have been solving equations and nonlinear equations for a long time, but whenever I say let's solve an equation, many of the times it's at the back of my mind that there is the solution. However, you might have several solutions. So can you somehow generically then tackle that problem? So you write down this is thing called a generalized equation. And so all of this, even the word operator, ultimately it comes from people generalizing their linear algebra intuition to the nonlinear world. So the goal is to solve that generalized equation, which is also called an inclusion, and we have been doing that all the time, right? Because convex optimization for us, or optimization depending on how partial of f is defined, that's the whole subject. It's just trying to solve those equations. So we're just trying to find a 0 that lies in the subdifferential. So it just helps. It's just a different way of denoting what we've already been doing. So far we haven't gained much. Soon we'll try to see what we can gain from this notation. So some basic things working with relations, I'll just call them operators now. You can define some simple algebra on them: addition, scaling, inversion, etc. So this is standard. the most important operation is called resolvent. If R is some relation with some parameter lambda, this inversion is called a resolvent, and we'll see we actually know a fortiori why it is called a resolvent. It resolves an equation for us, but let's see now why do we actually care, and actually we have been caring about this throughout today's lecture already. So we have been caring about that in the context of a certain special class of relation. So these arbitrary tuples, which are subsets of Rn cross Rn, most of them will be useless. Without additional properties, we might not be able to use them. So one of the most important properties, very wide-ranging, very important property that we impose on relations, which makes them easier to deal with, is called monotonicity. And the set valued operation is called monotone, or let's say operator is called monotone, if it satisfies this inequality. So let's see maybe simple examples. If A is a positive semi-definite matrix, then that holds for it. So it has that monotonicity property, right? Now subdifferential of a convex function should verify that that satisfies this property. That is equivalent to f being convex, subdifferential being monotone here. On Rn something more happens, but it's not so interesting. And actually projection and proximity operators also satisfy this monotonicity property, and you have seen that in the prox operators lecture when Yao-Liang probably talked about non-expansivity of prox operators. So this monotonicity property is really important, and one way to maybe think of it is that if I were to ask you, create for me some interesting generalization and of the notion of monotonicity, but in the world of vectors, you could come up with various generalizations. Some of those generalizations will be useless, some of those will be very useful. This is one of them. This is not the only way that people have thought about generalizing the idea of monotonicity or order into the world of vectors. So the abstraction essentially has been, people started first playing with semi-definite matrices, then they went to subdifferentials, and they tried to build on that intuition, and they saw that, okay, this monotonicity property is really important, but it's just another way of saying function is convex. So now let's try to first easily establish if R is monotone, then its resolvent is also monotone. That is, whatever is written here as an exercise, it's good to do that. It takes maybe not more than 1 or 2 lines of your paper, but it's worthy of an attempt to just get familiar with the notation. Okay, so now the importance comes back here. That's why I said the resolvent is so important. We're trying to solve this inclusion. So we're trying to solve this generalized equation. And we already saw that solving a generalized equation includes all of our optimization as a special case. So now you write that generalized equation there. Do the same thing that I did maybe on slide 1, but now it makes more sense. So you want to solve that. You scale it by some number alpha. You add x to both sides, and now you can invert. So you might say, where am I getting this from? And where am I getting this from, or why am I talking about this is actually told in that theorem. So if I write down that inclusion, 0 belongs to R of x, and I ask you to solve it. Well, one way for you to solve it is x is equal to R inverse of 0. Maybe that R inverse is easy to compute in your case. Maybe it's not. So if it's not easy to directly compute that R inverse, can we still add some regularization, do something that we are accustomed to doing to figure out how to invert that? I just want an x which solves that inclusion. And a common underlying thread for all of these optimization methods that we are developing is to somehow turn the problem of computing x into a fixed point equation. So an equation that is at least satisfied at an optimum or at a solution, and then try to see from that I can pull out an iteration. So that's all that this exercise is doing. It's starting with that generalized equation, turning it into a resolvent equation which has x on both sides, which suggests that, okay, maybe I could now run a fixed point iteration. And if R is monotone, its resolvent is monotone. So if you do some repeated iterations with a monotone object, chances are you might generate sequences which are well behaved. That's why we are talking about these general ideas. And this is what actually happens. So let's actually use this. So let's rederive this. What we did on slide 1 is to let's rederive prox gradient. So you have fx plus h of x. You write the inclusion. And now do the magic of the last slide. Add x to both sides. Scale or add x to both sides. Because we are trying to get a handle on the set valued creature there. And now you see, hey, this is just the resolvent operator of the subdifferential. So in other words, resolvent of subdifferential is prox operator, which also very clearly shows you or that why this prox operator object seems to be so important. Ultimately, its importance comes because it is resolvent of a subdifferential. And optimality of a convex function and all of its information is just captured in that subdifferential. That's why prox operator ends up being so important also. It's just a different way of talking about the subdifferential. So this is how you create proximal gradient. Now let's use this language a little further to talk a little bit about proximal splitting methods. And what are these proximal splitting methods? So I just wrote a sum of 2 or 3 functions in there. Suppose L is differentiable but the other 2 are not. Now try to apply proximal gradient to this. When you try to apply proximal gradient to this, what happens? Well, you need to compute that resolvent, right? Or in other words, the prox operator of f plus h. For example, so this is, this is say L of x, quadratic loss function. This is f of x, and that's the second guy that's called discrete total variation operator or function or whatever. It might not be easy to directly compute the resolvent of that. This is just a toy example. You can make it arbitrarily more complicated. The point being, maybe coming back to what you're more familiar with, in many of your statistics or machine learning problems, sometimes you have more than one regularizer. One regularizer is really enforcing a lot of structure, like here we are trying to get discrete gradients. The other one is trying to maybe smooth out, regularize, or make the conditioning better, or it comes from your motivation on proving generalized bounds or God knows what not. But when trying to do optimization, more than one of these guys makes life a little tricky. So the good feature of such a problem, however, is that individually the prox operators of these are really easy. And the whole idea of proximal splitting is centered around this resolvent or this prox operator is hard to compute, but these are easy. And Yao Liang probably told you actually an if and only if when you can make this super easy as just a composition of those two, but almost always you can not do that. So because you can usually not do those nice, you cannot easily handle that, but you can often easily handle the individual components. You want to be able to exploit that, which gives birth to this entire area of proximal splitting. So let's derive a fixed point equation. This one is all of it is going to be now manipulation with the symbols I've defined. There is nothing special happening, but it's very creative manipulation, not from me, from the guys who created that, okay? So assume now I just threw away that L plus f plus a. Just let's look at fx plus h of x, where both f and h are convex, but say both are non-differentiable. And I want to solve this minimization problem. I'll show you how to do splitting to solve that. And we are implicitly assuming that subdifferential of f plus h is subdifferential f plus subdifferential of h, and we are assuming that this subdifferential is non-empty. But that's a qualification condition. Most of the time people don't speak about it, but I'll show you later an example where it is important to keep that condition in mind. So we are solving that. Let's try to see. Let's play around with these things, and then I'll mention an open problem to the interested of you. So that's the generalized equation we are trying to solve. Now you have f plus h. We want to pull out resolvents or prox operators out of this equation. So what would be your first algebraic guess in there? Well, I just add x 2 times to both sides so that I can get I plus delta partial f and I plus partial h. Now, so now you have, again, this object plus that object, but you cannot still quite invert it. So splitting idea is really very simple. It just says, when in doubt, introduce more variables. So common trick people use. So let's write the latter guy by introducing a new variable z. So if z belongs to I plus partial h, that means x is prox of z by just inverting that operator, right? So maybe I'll just write it here in case you don't have it in your heads quite yet, is I plus lambda partial h inverse will be the same as prox of lambda h. So that's what I am doing there. Okay, so far so good, but let's see what happens. I tried playing with several such manipulations. Sometimes you can come up with new iterations by playing around with these manipulations, but most of those don't work. So now I have another variable 2x minus z, and if you think purely algebraically at this point, what am I trying to do? I am trying to get a fixed point equation which has the same variable on both the left hand side and on the right hand side. I will beat it until it confesses to that particular form, and it's not always easy to do that. So okay, so that means, well, that means x looks like the prox of 2x minus z, but you have both x and z on the right and x on the left, so it's not quite yet in the form. I should have written that equal to, sorry, not includes, but so it's not a fixed point equation yet. So we need one more idea. So that one more idea is based on introducing slightly more notation actually, but other than that, this 2x minus z is half the way. So that thing is called a reflection operator. So if you have a prox operator, 2 times prox minus identity is called reflection operator. I try to draw a picture. I don't know. I don't think of these things so pictorially, but maybe you can think if prox is nothing but projection. So this thing x projects down here. You're reflecting about this line. I guess that's where the reflection should be. 2 times that will be probably there. I don't know if you like to think in terms of vector calculus. So that reflection, but that could be misleading because that is only with projections. It's called a reflection even though it's no longer really a reflection because this is a prox operator, it's not a projection operator. But the idea came from there. So now there is something called Douglas-Rachford method. I'm telling you about this method because actually for those of you who've seen ADMM, ADMM is in some sense a special case of Douglas-Rachford method. It's not so easy to show how exactly. We will see that maybe soon, not in class, maybe on homework or in the next lecture, depends on my mood. But it's a nice identification. So Douglas-Rachford, these guys were actually solving partial differential equations in applied math in maybe 60s, doing a lot of linear algebra. They came up with some nice iteration, and that iteration has been over the years then generalized, and this is what it is. So let's see, if z belongs to that set, that means by inverting x is prox of z. So far so good, that's our notation. That means the reflection operator of H is nothing but 2x minus z, right? You put 2 times here, subtract z, 2 times, so you get that identification, which is beginning to sort of look nice because 2x minus z was on the previous slide and now we have hidden it inside R. So back to what we were doing, we had this inclusion, we added x to both sides, we replaced that by z and we said 2x minus z belongs to that. So now x is prox of f applied to reflection of z. Why did I write that? Well, I just replaced that, simple substitution. But alternatively, I find this rather shady to be doing it this way. But RH of z is 2x minus z. So another way of writing z is 2x minus r, right? So the crazy thing is once you try to derive fixed point equations, you have to manipulate symbols in various ways until you hit something that looks like a fixed point equation, and then it might not work. So you have to try again. So this 2x now replace x. What was x? X is in terms of prox f applied to r. So you replace x by that, and this z is already there. So now we have z on both sides. So you actually get 2 times prox of f applied to some vector minus some vector. Hey, but what is that? That is just the reflection of operator of f. So now we managed to massage that inclusion into a fixed point type equation, z is on both sides. So now we are almost there. It's not quite yet done because we have to still say what's happening with x, right? So the optimality condition, what we have done is we've rewritten the optimality conditions, because see, this is just manipulation of the optimality conditions. We have rewritten those two, that x belongs to prox h of z and z belongs to that repeated reflector. So using that, turning that pair of optimality conditions into an algorithm, that is the Douglas-Rachford algorithm. So slight more work is needed. So it iteratively solves those two, but with some more creativity than is there. Okay, so you just run that. So it comes from there. And then one can prove, I'm not going to do that here. If anybody is interested, I can point you to the proof. Douglas-Rachford is currently one of the more popular methods to analyze, but it is somewhat tough to analyze. Its complexity is not fully understood quite yet. So if it, but you can show, but it's important to note, what am I showing? You might have thought that I'm iterating z, that my convergence statement will be about z, but the convergence statement is actually about the x's and the v's. So this has happened to me many times when I program Douglas-Rachford. I output the solution and the solution is wrong. It's because I often by mistake just end up outputting z. You have, the thing that converges to a solution is the x. So this x and this v, they converge to solutions, z does not. Quite interesting behavior. So if gamma k, this is like some kind of step size. So one good thing is usually in Douglas-Rachford we don't need step sizes. So I'm going to eliminate step sizes. So let's pick gamma k equal to 1 so that there is no step size tuning in my method. So you pick gamma k 1, well, you simplify those equations. There's nothing special. So I drop the superscripts. I'm going to write it in a very pretty form. That's the form I like, because then you can implement it in 3 lines of MATLAB. So let's get it into the 3 lines of MATLAB form. Well, it's already in 2 lines. So what we have done is we are iterating z is t of z, where t is that operator, right? It's just a very simple manipulation of the last line. So a little small exercise, very nice exercise, is to just rearrange this stuff so that it looks like averaged reflections. So the Douglas-Rachford method sometimes is also called the method of alternating reflections or alternating averaged reflections. So it is intimately connected to the method of alternating projections, which is a very famous method from von Neumann's time. This one is somehow, it's doing alternating reflections, so actually often it works much better than alternating projections, not always. Theoretically it's actually slightly inferior, but in practice not. So there's a, Anyhow, this little exercise is quite pretty. It gets it into this really nice reflector form. So let me just show you now. Okay, this is the part you can implement in 3 lines of MATLAB. Okay, conditioned on the assumption that you have available subroutines for computing prox operator, and the subroutine maybe takes 1,000 lines to compute. That's not my problem. So, okay, so let's see a setting where Douglas-Rachford does not really apply, but you still want to apply it. So we got trapped in that setting. So suppose I'm trying to minimize indicator function of a convex set plus indicator function of another convex set, which is the same as trying to find a feasible solution in A intersection B. But what if A intersection B is empty? Just because you want to solve a feasibility problem doesn't mean that there is a feasible solution. So especially in this case where there is no feasible solution, but you still, and you try to solve this. So what happens here is, by definition, Douglas-Rachford cannot be applied. Why? Because the subdifferentials of the first function plus the subdifferential of the second is empty. So Douglas-Rachford doesn't apply directly. But there is a very nice work by Bauschke and Combatz. They show how you can still apply. So this is a subtle point that gets lost many times. That's why I'm telling you in class already, that you can still apply Douglas-Rachford, and a crazy thing happens. I don't have a picture for that. Stephanie has a picture for that. You can apply Douglas-Rachford. It will generate diverging iterates, but from those diverging iterates you can pull out a shadow sequence that converges. What does it converge to? Well, converges to exactly what you would desire it to converge to. So you are trying to solve, you have a convex set A, convex set B, they don't intersect, and if you try to run Douglas-Rachford with the Bauschke-Combatz magic of extracting shadow sequences, which is fairly easy, you actually converge, you solve the so-called best approximation problem. So you do not solve the convex feasibility problem because there is no feasible solution, but you solve the best approximation problem. That means you find a pair A and B which has smallest distance. A lies in convex set A and B lies in convex set B. So means, and we used it for some application very recently at NIP. So I just said I'll show you. It's a nice example of using Douglas-Rachford, even though actually theoretically in all the typically stated assumptions it's not applicable directly. So there's another example of a best approximation style problem. We minimize the square distance to set A plus square distance to set B. Remember, you proved distance function to a convex set is convex on one of your homeworks. This is just that. So, well, you can take those and try to minimize. Very pretty thing falls out. So the part of the exercise I leave there, if the reflection operator for squared distance is nothing but projection operator. That's a very interesting, I didn't foresee it until I did the algebra. After you do the algebra, then you can try to say, oh yeah, okay, but you know, that's quite an interesting thing that it satisfies. And if you then apply that alternating reflections, you actually get alternating average projections. So when trying to minimize sum of squared distances for a best approximation type problem, you do not quite recover alternating projections via DR, but you recover something very similar, which means its theoretical analysis could be done using the way you try to do theoretical analysis of alternating projections. But I'm just saying could be done. I haven't done it, only did it partially. So it's, I'm guessing in good cases this might even converge linearly. Okay, so I think, well, I have some more time, but I think I'll cover this next time rather than this time, because this will take us into class of problems where so far we had only fx plus hx, but now I have a sum of several of these guys. So I think I'll defer a coverage of that to the next lecture, and we'll start looking at several different ways of solving these problems. Some of those are easy to parallelize, some of those are not easy to parallelize, but we look at several different ways because a lot of the machine learning literature is full of this type of problem. So I'll put these slides online so you can look at the details. But one thing I wanted to mention at this point was this particular iteration that we have here, only very limited results on its rate of convergence are known. So there is a 1/k convergence rate paper which is from 2012. Under some other assumptions, people are trying to analyze its convergence, but its convergence is not fully understood. A very interesting thing is there's a series of papers by Jonathan Borwein and his students and postdocs. Jonathan Borwein is a master of, I've probably told you previously, master of all things convex and also in general of lots of math. So they found that they actually implemented a Douglas-Rachford based method to solve Sudoku, which is not really a convex problem, and it's working somehow really well. So they're trying to understand, it seems that even for certain discrete optimization problems where somehow the discrete set has a permutation or a sorting based structure, it seems Douglas-Rachford style methods seem to work even there. But analysis of the non-convex version is much, much harder. We looked at in our NIPS paper at just using it as a subroutine for submodular minimization, but there, even though the ultimate problem is non-convex, it has a nice convexification, so it's not as crazy as the example of Jonathan Borwein. But it's a subject of current research to understand this method, and you can think of other things like coming up with an online version of that or scalable version, etc., etc. But this method sometimes works much better than methods like proximal gradient or accelerated proximal gradient. Sometimes it does not, okay? And regardless of what you read in papers or regardless of what others tell you, at least from my class, I want you to go back with the message that despite theoretical claims, there is going to be no optimization method which will win in all problems. It's a very obvious thing, but people forget this very frequently. So what is more interesting is to have a bunch of methods and try to see on which kinds of problem classes they work better. So I think with that, I'll stop and see you on Wednesday. Yeah.
Could you just describe geometrically what this shadow sequence argument is?
The proof.
No, just using the proof, or just what the idea is using that figure that you do.
So the thing is, in one of our talks, we have actually a nice animation of that to show you that somehow the z that comes out from applying the Douglas-Rachford operation, somehow the z that comes out seems to somehow start diverging to infinity. But the shadow sequence is obtained by projecting z back either onto B or onto A. So even though it is running away, you pull it back, and from what you pull back, so it's not 100% clear though. So the thing is, in some sense, one of the vectors is running off to infinity, and there is another one which is in some sense running off in the opposite direction. So when you add them, those bad infinities cancel out and you actually land at the solution. That's roughly what happens. But I think I'll show you the actual MATLAB visualization to actually see this behavior. But it's still mysterious to us to fully understand why it works. As in, I can understand the algebra, but I don't understand the geometry of it fully. Okay, so guys, do remember to upload your midterm project report.